So the talk I'm going to give today, it's called T-Reqs. It's going to be on HTTP request smuggling with differential fuzzing. It's new work that we started a while back, about a year ago, and I'll be talking about that. Just brief on my background. So I did move to Northeastern University in 2011. I was faculty in Europe before that. So right now I've spent maybe half of my career in Europe. I was at the Technical University of Vienna and Institute Eurocom. The other half has been in the US. And I've been mainly active in malware, as Arun mentioned, since 2004. In general, I'm interested in trying to secure systems of all sorts, but I've also been interested in web security since 2004. So I started working on web-related issues and malware-related issues about 15 years ago or so. And I've been continuing to publish in these two areas. But in general, I would say I'm a practical security person. I'm interested in attempting to create solutions for practical security problems. Ideally, they have a potential to impact real people. So in my talk today, I actually debated between talking about some general idea or presenting something specific. So when I was creating this talk a while back, I was thinking, okay, should I talk about maybe web in general or malware in general? One idea could be to talk about web security and to talk about where I think things are going and what the interesting problems are. Or, I have one talk that I prepared a while back about my one-time experience in taking a real technology and transferring it to industry in a spin-off company. So I can't say I've done this, multiple times, but in the last decade, I worked with Chris Krugel, as Arun mentioned, Giovanni Vigna, and we were able to do this. So I have some experiences there. But I also thought about speaking about something malware related. But then I decided that, this is an interesting topic. So I decided to talk about a recent ACM CCS paper. It's a simple problem, relatively simple, but I think it's an interesting problem that has real world impacts. And that actually, again, affects a number of companies, a number of users out there. That's why I thought, okay, this might be actually interesting to talk about. So the work I'm presenting today was led by my PhD students, Bahruz Jibiev and Steve Sprecher. It was actually their idea. They came up with this. It was co-led and mainly directed by my former student, Kaan Onarlıoğlu from Akamai. And Kaan's contribution to this work was actually essential. It was very important. He is the CDN expert, right? He works at Akamai, so that was very, very valuable for us. All the insights he had, understanding the problem space, that was very useful for us. And I was basically lucky enough to be involved and to work with these smart people, right? That was my contribution. I have to say, most of the work, the credit goes to them, right? It doesn't go to me, but I'm basically presenting their work because I think it has, it's quite interesting. So the talk I'm giving today, as I mentioned, appeared at ACM CCS in November. In case you'd like to read the full paper, it's called T-Reqs, HTTP request smuggling with differential fuzzing. And it's available on the internet. You can download the full PDF if you're interested in the technical details. And right now, of course, we're working on follow-ups to this topic. Hopefully, I'm hoping that they will result in interesting papers as well. So what is HTTP request smuggling, right? If you look at this problem historically, so what I'll do is I'll basically explain what that problem is, and then we'll look into what we actually did in this space. The problem of HRS has been around for quite a while, right? It was first discovered in 2005, and since that time, right, 2006, 2007, this is actually one topic that I typically talk about in my classes. So when I teach system security, HRS sometimes, has a couple of slides because I always thought, it's an interesting problem. I thought it was maybe a smaller issue that people don't typically think about. But when I talk about input validation, this is something that I often mention. I say, hey, there's also this problem called HRS, right? Interestingly, though, it started to gain attention again quite recently. James Kettle, is an industrial researcher who also has created a bunch of tools. He has created the BURP, web security tool suite that some of you might actually know, gave a black hat talk in 2015. And he talked about this problem. He talked about HRS, and he talked about how HRS can be used to, attack companies like Akamai, a bunch of CDN providers out there. And he showed that this actually has real world impact, right? After 15 years, he sort of showed that, yeah, this is still a problem. And the internet landscape has changed, you're just seeing this problem be even more important than it used to be in the past. So lately, though, the focus has been mainly on transfer encoding versus transfer length discrepancies, right? Which is something I'll be talking about in depth. I'll show you an example. So that was the main focus of, you know, a lot of the talks out there, Black Hat presentations. But we took that a step further and we sort of decided, okay, let's actually look at this scientifically and let's try to detect these things automatically, and let's try to see how much, you know, how many bugs out there we can actually discover, right? But in terms of HRS, it has been rediscovered, and people have been reporting HRS vulnerabilities. They have been finding bug bounties. And if you actually look at, you know, CVEs that people have reported, you'll see that, you know, last time I checked, well over $70,000 in bug bounties were paid out, right, to people who've actually discovered these vulnerabilities. So what is HRS, right? It's actually a relatively straight problem, right? It's a vulnerability. So on the internet, if you go to DuckDuckGo, which is my favorite search engine, that's the search engine that I use, and you know, Tor uses as well. If you type something like funny cats, right, and you'd like to search this, your browser would actually send a request such as this, right? So you would have a GET request with a slash. It would have, you know, it would send this entire thing in HTTP 1.1, you know, which is the most popular protocol out there. And then the request would tell you that you're sending this request called query is equal to funny cats, right? Funny plus cats. And the content length is 16, right? So basically you're telling the server that whatever you're sending to it has 16 bytes in length, right? So that's one way of sending this HTTP request, right? Which is very popular. So your server or your client might have actually implemented this request using content length. So you have a request line, you have all these headers, and you have the request body, right? At the same time, you could send the same request using transfer encoding, right? Which is another HTTP, you know, specification. Just a heads up, I think my video is freezing a bit. Can you still hear me? If anybody can confirm my voice is coming.
Yeah, it's loud and clear. Thanks.
Okay, perfect. Thanks a lot. So another way of sending this could be using transfer encoding, right? So there are different encodings, but chunked encoding would mean that I basically would send, you know, this in chunks, the same information. And every chunk I'm sending, this is a query, I would say, well, I'm sending 6 bytes, right? For funny cats, the hexadecimal length of this would be A, right? So there's another way of sending all this information as well, right? But these are pretty much semantically identical. You're doing the same thing, right? So either content length or transfer encoding. So the question is, what would happen if I would send a request that would actually combine both of them, right? I send one request, and in this request, I say transfer encoding is chunked, but I also say there's a content length of 16, right? This is not part of the specification, right? Usually you should only have content length or you should only have transfer encoding, right? But if you actually combine both of them and send a request, the question is what would happen, right? And this actually can lead to this HRS, request smuggling vulnerability. So if I create a request like this, and I say the content length is 64, and I also say content length is chunked, and I provide this chunked encoding body, right? And after this, I put a bunch of A's. What could happen is that if I have a reverse proxy, which is a typical scenario on the internet today, right? You have something like Akamai that accepts requests on your behalf, and then they would forward those requests, they do a bunch of analysis on it if they wish, and they would send it to, say, Apple, or they would send it to Bank of America, right? There are a lot of CDNs on the internet that do load balancing for you. So the reverse proxy, suppose this is Akamai, would take this, right? And it would actually see the content length because it's more interested in that. That's the way it's being implemented. And it would treat everything, the body, as a content length of length 64, right? It would forward this request to the origin, but this time the origin might be implemented differently. So the origin might actually look at the transfer encoding, which is chunked, and might assume, okay, this is, you know, the transfer encoding here is chunked. So it would just take the body, which is funny cats, but you then have a bunch of A's left over, right? So this is basically the request that you smuggled just because of the discrepancy between the implementations of these two servers, right? According to the HTTP specifications. So right now you have a bunch of A's. Well, this request would be sent to the origin. That is not a valid HTTP request. So the origin would probably generate an error message in this case, right? It would say, I don't recognize this, header. I don't know what this means. An error message would be generated. So right now, nothing really bad has happened, but you were able to, inject all these extra bytes that would sort of confuse the origin server, right? Because it looks like a request header, but it's actually not, right? So nothing too bad happened right now, right? But instead of saying this, right? Well, after the AAAs, if you would actually send another request, right, for dogs, the origin actually has AAA, then has another valid request, but the AA is not a real request, so it generates an error message. But instead of doing this, you could also smuggle a real request, right? So what would happen if you say get ABC as a part of your body, right? The request that you're smuggling. Well, then the origin server would actually have two requests, right? But so your reverse proxy basically thinks it's one request, right? But you're able to smuggle these extra headers to your origin server, right? So you're able to request another extra page. Of course, the question now is, so what, right? So you're able to do this. You're able to inject these extra headers and extra requests, but where's the problem here, right? So people have demonstrated that using this strategy of injecting extra headers, you can launch attacks such as response queue poisoning, right? So if you have a bunch of people who are requesting things from your reverse proxy that are being sent to the origin server, if you're able to inject an extra header, then you would actually have the wrong page be delivered to one of your users, right? Because you're just bringing the servers out of sync. I'm injecting this extra header. So if somebody goes to CNN.com, they might actually be served the page for an attacker. So they might actually be seeing the page of attacker.com, right? Which is not a good thing because, you could launch a phishing attack or you can launch some other attack, right? So that's one possibility. People have also demonstrated that using this technique, you can do web cache poisoning. So I can actually have a bunch of requests being sent, right? But if I'm able to smuggle something, I can change the caches and I can change the mapping between, again, CNN and say attacker.com, right? So every time somebody goes to BBC or CNN, they might be served the page of attacker.com, which has been cached, right? People have also demonstrated that using this technique, you can bypass security controls. So if I'm looking for specific headers or specific body content, right? And if I'm able to smuggle in a request, right? The reverse proxy might actually look at the headers, but it doesn't see the header that I'm actually injecting as a header. It's part of the body. So, I might actually be missing it, right? So although I'm not supposed to send, or request a specific page, I might actually trick the reverse proxy into downloading that page, right? Because the origin is basically getting it. So you can come up with a bunch of scenarios like this. For example, in March 2020, there was a bug in Slack that people reported, and it created a $6,500 bug bounty where using this trick, they were able to bypass some of the controls that Slack had in place, right? It was an HRS attack. So what this tells us is that discrepancies in body parsing behavior of servers can be used for HRS, which can then pave the way for a bunch of different attacks like the ones that I've been demonstrating, right? So HRS is a reality, and yes, it can create problems. So what are the research questions we were trying to tackle in this work? Well, first, can you actually systematically test for HRS at scale? What technology stacks are at risk? What parts of a request can induce body parsing discrepancies? And what escalates a body parsing discrepancy to HRS, right? Just because you have these discrepancies, the question is this going to result in each HRS vulnerability, right? So there are a bunch of interesting research questions to answer here. So we started by first asking ourselves the question, can we systematically test for HRS at scale, right, for many, many products? And what technology stacks are actually at risk here, right? So, the combination of Akamai with some Apache servers, is that a problem? Is that a realistic problem, for example? So before we go into that, we also thought about availability and the ethics of this work. So T-Reqs is open source and it's available on the lead author's websites. A bunch of people have downloaded it, and we know in practice, some people have actually been using it. In terms of ethics, we conducted the study within a controlled environment. We did not launch any attacks against external entities. So we did not go and, Cloudflare or some other company did not actually attack them. We performed responsible disclosure to all vulnerabilities that we discovered. And we also provided the copy of the paper and data to all affected parties before the publication of the work, right? So we basically set up everything in a controlled lab environment, and we did all our tests there. As I'll discuss later, when we were doing measurements, we did everything, thinking about ethics, because you don't want to actually launch these attacks against real companies. So one idea that we had that we decided to use was differential fuzzing. So fuzzing is a well-established software testing approach, and differential fuzzing aims to determine differing behaviors between applications when given the same input, right? So we thought, hey, this is actually suitable for our purposes. If we can feed input to different implementations of web servers, then we can compare how they're actually dealing with these inputs. Well, differential fuzzing can be a promising technique here. Differential fuzzing in the past has been used for side channel identification, violations in TLS libraries, etc. So people have used it for different purposes. So we actually decided to use this for detecting HRS. We thought, hey, this could actually be valuable for HRS as well. So the idea here is to generate inputs as a first step, right? So we do know how headers are actually structured, right? So we have a GET request or a POST request. We have headers as a part of the HTTP protocol. You can have content length, you can have transfer encoding, and you have a body, right? And you can actually break these up as tokens, right? You can work with context-free grammars. We actually exactly know how these requests are structured based on the HTTP protocol and the RFCs, right? And you can go through all of these, and based on them, well, you can actually come up with fuzzing heuristics or algorithms that generate inputs for you, right? Random inputs, but that hopefully make sense, or sometimes actually do not make any sense. So, you can basically vary things like, is it a GET or a POST request or a trace request? How does the URI look like? Is the protocol HTTP or something different, right? Or also you have versions which could be 0.9, 1.1, 1.11, or what happens if you actually leave that out? Or what happens if you provide, that the protocol is 0.5, which would be invalid. So all these things you can actually specify in your grammar, and then you can start generating inputs. You can also start mutating the inputs, right? Once you've generated initial inputs, for example, you have a trace/EBC here using the protocol 1.0, but you could do string mutations on that, right? So what happens if I take a trace but insert a slash there, right? Which is invalid. But how would the server react to this, right? What would happen if I leave out the B or, replace that with a question mark, right? How would the server react to that? Or instead of a dot, I leave it out and I say HTTP version number is 10, right? Which doesn't exist. So you can also do tree mutations. And in this case, it means that you can actually leave out certain key tokens. Like instead of trace, I would leave it out, or I would write HTTP, right? Or I would put something completely different, right? So you can come up with straightforward heuristics and algorithms that would generate these inputs for you. And that would then send them to a server. And the idea there then is to understand, okay, what does the server do with these random inputs that you're generating? So in the experimental setup, as a first step, what we did was we had the input grammar that allowed us to generate a bunch of inputs. We take these inputs and we mutate them, right? Using our algorithms, using our fuzzer, just like a typical traditional fuzzing algorithm. We send these inputs to the HTTP server, and the HTTP server here is everything we could get our hands on, Apache, HTTP, Nginx, Apache Tomcat, HA proxy, Squid. These are all, software that you probably heard of, but Varnish, all popular software out there. And then, of course, we're generating these inputs and we're sending the inputs to these servers. And as a first step, we're trying to understand, okay, what does the server do with this input, right? How does it process it? How does it forward it, right? Then we look at the forwarded requests, right? We have a feedback server, and we simply store these, the inputs and the results in a feedback database. Was there a question? If somebody has a question, just feel free to speak up. Okay, I guess not. So as a first step, we have this experimental setup. We're generating lots of inputs. We're sending it to the servers. The servers are forwarding them. We have a feedback server, and the feedback server, all that it does is it puts all these requests that we're forwarding into a database, right? This is the first step, because we're trying to understand what happens if I put these errors into the request. Does the server ignore them? Does the server forward it? And if it forwards it, what parts of the request does it forward, right? We store everything in a database. So the second summary is that T-Reqs fuzzer and the experimental setup actually let us systematically analyze the body parsing behavior of many of these servers, right? First step, generate inputs, send it to the servers, store the results, right? The second question is, what parts of a request can induce body parsing discrepancies between these servers, right? So that's what we're trying to understand. And what we're trying to understand here is we're looking at the request line, we're looking at the request headers, we're looking at the request body, and we're trying to see how these servers are dealing with it if you have variations of the request line, if you have errors there, right? How do they deal with these errors? So if you look at the request line, what we actually ended up doing is after storing all this information, all these requests in a repository, right, in a database, we have the opportunity now to compare the different technologies, right? So what happens if, Cloudflare received this very concrete, request, right? How does it deal with it compared to how Tomcat deals with it, right? Are their behaviors different, or are they doing the same thing, right? How does Nginx compare to Apache? So in this graph here, you basically see, and in the paper, we have more details of this. There's a detailed description of all the different, inputs that we generated. So there are things like mangled method, distorted protocol. What happens if you invalidate the version number, right? But this graph actually allows you to then to compare. So you can actually check Squid versus HA proxy, and then you're able to see that, that they apparently react differently to different version combinations. Or you will be able to see if you're mangling the method, right, in the header. Well, it looks like Squid and HO proxy have different behaviors, right? They don't have identical behaviors. Their behaviors are actually different. So we did this for all the the inputs that we were generating for the request line, things like the distorted protocol. In this case, what happens if we, instead of HTTP, you replace the H with a P, right? What would happen if we mangle the method, right? So instead of a get, we just put a dot there, right? Does that lead to unexpected behavior? Or what happens if I just get rid of the method, right? Instead of that, like get, I have nothing. How does the server react to that, right? Or we do multiple mutations, right? So we have a bunch of tests like that we describe in the paper. We send it to these servers, and it allows us to compare the different servers and how they actually react to this, right? And we did this for all the technologies that we're actually analyzing. So as a first step, this allows us to see how the different technologies compare to each other with respect to their behavior, right? So you're not finding any bugs yet, but you're actually seeing how they react to these inputs. Of course, we did the same thing for request headers. Again, if we had graphs like that that allowed us to compare, for example, double transfer encoding. What happens if I inject the transfer encoding twice? How does the server react to this, right? Which one do they actually take? Do they take both of them, or does it result in an error, right? Or identity encoding or manipulated termination. So again, you're able to compare all these technologies with each other, and you're able to see what inputs actually create discrepancies between the behaviors of these servers. Similarly, for the request body, we had a bunch of different input generations, and we tested the technologies. So if you actually take a look at Akamai specifically with respect to different technologies, if you're doing things like getting rid of \r\n, which we call chunk data termination, what looks like for a lot of technologies and Akamai, the behaviors are actually very, very different, right? Which is something that maybe you wouldn't expect. But in reality, if you do things like chunk size termination, where you inject a \t, the behavior suddenly change, right? So we did this for all the technologies as well, right? So as a first step, at least we have some data now, well, as a second step, that allows us to see how these technologies are reacting differently. So the third summary is mutations in all parts of the HTTP request, things like the request line, headers, and body, can cause discrepancies between the servers. So in real life, if you do an experiment like this, you're going to see that for a lot of requests, the way these servers are reacting to these requests that are, sometimes erroneous are different, right? They exhibit different behaviors. So the last research question that makes it interesting for us is, what escalates a body parsing discrepancy to HRS, right? The fact that these servers are exhibiting different behaviors, does that mean that you automatically can do an HRS attack, right? Which is something that we wanted to understand. So how do you test for HRS? So the technique we used was inspired by previous research. So we put each pair is put together in a proxy and origin, right? Suppose we would like to test Nginx versus Apache. So we put these, we set up these proxies or these servers in our test environment. And we actually try to inject a smuggling request. And right after we smuggle a request, we send a benign request, right? And we actually basically do exactly what I showed you at the beginning, where we were injecting a bunch of A's, right? Which is a classic test. So if the server basically generates an error message and says, I don't recognize this request AAA, I don't know what this is. Well, this error message actually indicates that whatever we injected succeeded, and it's actually creating an error message, which basically means that, yeah, that server is very highly likely vulnerable to HRS, right? So this actually allows us to test for HRS without actually launching a real attack, right? But actually allows us to see, yep, there's very, very likely if you launch a real attack, that's going to work, just because we were able to inject these extra, characters into the other server. We of course wanted to also confirm HRS, right? A real HRS. And we were able to do this for, we compared a bunch of different servers. And if you look at Akamai versus HA proxy, we were able to detect, real HRS vulnerabilities because error messages were actually generated, or Akamai versus, ATS, using some of these combinations, generating error messages, we actually saw, yeah, this is actually indeed vulnerable to HRS. So if somebody would like to exploit it, in practice, they will be able to do this. We also compared Akamai. Why Akamai? Not because they were worse than everybody else, but because we had one of the co-authors who was working at Akamai. He had more control over it, allowed us to gain more insight into what was happening. But if you compare Akamai versus different technologies, these different behaviors would actually lead to real HRS vulnerabilities. And of course, as I previously mentioned, we informed everybody, and we tried to make sure that all these vulnerabilities were then actually fixed, that we were able to detect. So this fourth summary was body parsing discrepancies on popular servers are opening the door to HRS, real vulnerabilities that can then have impact in the real world, right? But of course, there are some failure conditions, which is also something we studied, and we described that in detail in the paper. What are the conditions where HRS looks likely, but it actually fails, right? It doesn't actually work. We saw that in some cases, the mutation is not preserved, right? This could be on purpose because the server is actually doing a good job, or it could be just maybe by luck, right? It's difficult to say. But if you're actually sending and injecting HRS, and that HRS message is sort of being filtered, and it's not being forwarded to your target server, well, yeah, in that case, the HRS attack obviously is not going to work, right? So we did observe this in some technology combinations because they were either doing a good job or it was just luck. There were some cases where some technologies, if they actually notice that something weird is there, like an HTTP request error, what they do is they just break that existing connection. And if you're actually closing that existing connection, it means that your proxy is not going to be able to submit more requests, which means that HRS is not going to be possible, right? You won't be able to inject more requests just because this connection has been broken and it needs to be created. Again, this could be good error handling behavior. It could just be luck. But there are some technologies out there that are actually doing this, right? So in those cases, HRS is not going to work. We also saw cases where whenever something weird was happening, the exit point was basically just clearing the entire request, right? We're just dumping all of it, which then means that, your attack, again, is not going to be successful, right? So we actually observed failure conditions as well, and we talk about them in the paper in more detail, just to give insights on when an HRS attack actually can be successful. So we also try to assess the impact of this, right? So the way to do this, of course, ideally, is to demonstrate possible attacks. Because if you're producing a paper these days and you say you found some vulnerabilities, right? People still want to see that you demonstrate these attacks, right? You find either unknown vulnerabilities, or they want to see, yeah, this is really an attack and you tried it out, right? So, we abused the chunk body parsing discrepancy between Akamai and Nginx that we had set up in our, environment, and we had Akamai, someone from Akamai, coordinating these attacks for us. So we configured Nginx to serve OWASP multilydia, which is a framework from OWASP that has a bunch of real vulnerabilities. And the scenarios we had were things like bypassing headers, hijacking requests, or delivering attack payloads like a reflected HSS delivery. And in this very controlled environment that we had set up with Nginx, we were able to use HRS for this technology combination to do all these attacks, right? Bypassing headers, hijacking requests, or doing reflected HSS, right? Just by combining HRS with XSS. So just to demonstrate that, yeah, the attacks that we are talking about are real, and they can lead to real vulnerabilities in existing systems, right? So they're not just something theoretical that people might complain about in an academic paper. So we also wanted to estimate server combinations, right? So just because Nginx is combined with Apache, is that actually a realistic combination in the wild, right? Is this something people are really doing out there, or is it just some, combination that we had in our lab environment, but not very realistic in the real world out there, right? So we conducted an experiment with Tranco 10K. So we wanted to measure and find out what server tech combinations are possible in the wild. So is it feasible that Apache is being combined with Nginx, right? Is it something that you actually see, or is it extremely rare that you would see a combination like that? So we used fingerprinting for identifying technology combinations, which is not perfect, but it gives you some indication. So, the result you can get in something like this is not perfect. There's no ground truth, but you get an estimation, right? So based on the estimations and the measurement we did, we could estimate that 17% of the sites in the top 10K use technology we have identified discrepancies for. So if we see that there's a discrepancy, say, between Nginx and Apache, just made it up, we could actually look at these measurements and we could see, okay, that's actually a realistic assumption. We actually do see this in reality, and there are real services that are combining these technology, which means that whatever vulnerabilities you're actually identifying, there's a good chance that they're going to be, it's going to be possible in the real world as well. So the summary of this part of the work was that body parsing discrepancies can be exploited for HRS only when certain conditions hold, right? Just because you think that Apache and Nginx has a discrepancy and you've seen it, it doesn't mean that you'll be able to exploit it in reality. Just because it's not a realistic, maybe, combination in the wild, or maybe Nginx does something and cleans certain requests and disconnects the connection, which means that it's never going to actually lead to a real HRS in real life, right? Just having these discrepancies gives you a starting point, but it doesn't mean that HRS will be possible. But for a lot of these combinations, and we actually did demonstrate that, yes, HRS vulnerabilities are very likely and they can be exploitable. So we did responsible disclosure. So we contacted Apache and they assigned a CVE for some of the issues that we found. Nginx implemented hardening measures based on the discussions we had with them, trying to fix some of these issues. ATS showed its willingness to add T-Reqs to their toolset. So they liked this toolset and they said, going forward, instead of waiting for us to use the tool for fuzzing, they're actually going to use it in their development process to discover real world vulnerabilities, they said. And CloudFront discovered holes in their defenses. They acknowledged it. Akamai coordinated a response with one of the co-authors, right? Because we had one author, as I mentioned, who was working there. Of course, it was valuable for them, right? So they were able to use these results to secure their systems and to make them better. So there's actually a lot to discover in this space. So there are non-standard HTTP headers one could actually also take a look at. There are non-default configurations. There's a high number of mutations. There are longer experiments you can actually conduct, right? So you could do a bunch of things, and we're doing some of them already. So you're looking at things like, okay, what about HTTP 2.0, right? The new HTTP standards, right? Do they have similar problems, right? And if so, what is the impact of that, right? But in general, nobody is really to blame, right? This is a very difficult problem to fix, sadly. The combinations of different technologies are creating HRS, not the individual servers, right? If an individual server receives, transfer encoding and content length at the same time, the way it chooses to deal with it, and it says, I'm just going to ignore the chunked encoding, I'm just going to look at the last header, which is content length, is, an implementation decision. And maybe an error message should be generated, but this is not always specified in the HTTP specifications, right? HTTP protocol specifications. It's not always a part of the RFC. And sometimes the RFC basically says, if you see an error, or unexpected behavior, do what you think is right? So it doesn't actually always specify what you should do, because it's very difficult to do in practice. And sometimes some of these server combinations or servers need to be fault tolerant as well, right? They don't want to just break a connection just because there's a small mistake, because it could be an honest mistake as well, right? So nobody is really to blame, which makes the problem much more difficult to correct in reality, right? So an open research problem is, unfortunately, that the reality is complicated. RFCs are ambiguous, bugs can become inevitable, and powerful mechanisms to rewrite HTTP requests are desirable and necessary features, right? So you do want to be able to forward requests for CDNs to work, right? You do want to be able to deal with some bugs. You don't want to just break all connections, because that could lead to performance issues. At the same time, RFCs should be perfect, but they are not, right? So how do you deal with this issue of HRS in this very complex ecosystem? Predicting, detecting, mitigating, or fixing HRS ends up being a non-trivial open research problem, right? Although it is not a very deep problem, if you think about it, and we've known it, it's been around since 2005, something I've even talked about in my classes. It's not really straightforward to fix. It's not, you can't just say, follow all these steps and then you'll do a great job. So solutions are required, and maybe even automation is required that would allow you to do a better job, trying to fix HRS in real life, right? So to conclude, in this work, we developed an HTTP fuzzer to systematically discover new HRS attack vectors. We designed an experimental setup for more complete and effective testing than previous work. People have just looked at, content length in combination with transfer encoding. It's a very simple idea. They actually show that you can do a bunch of other things that will lead to HRS, not just this relatively simple trick. And we also provided insights into the conditions for a discrepancy to be used for HRS. Just because you find a discrepancy doesn't mean that you're going to have HRS. We try to analyze, okay, what leads to a real HRS in real life, right? And we showed the possibility of HRS attacks on popular servers. And our work, we were happy to see, led to real-world discoveries of problems and their fixes. And right now we're working on follow-ups, and we're even trying to come up with an HRS defense, because right now, if you actually come up with good solutions, I can tell you many companies like Akamai will be interested, right? Because they know this is a problem and they don't exactly know how to fix it. And there's also the legacy problem. You can't just replace old servers or tell them to do specific things, because the entire internet would then break, right? Which is unacceptable. So you're also dealing with the legacy problem at the same time. But being able to detect the HRS might actually be valuable. It might actually be nice. And with that, thanks very much. If you have any questions, I'll be happy to try to answer them.